Welcome back. It's Jeff again. We are continuing to explore our electronics learning laboratory kits we're going to use for electrified linear systems experimentation. In this video, we're going to follow up with more discussions about breadboards and focus on connecting resistors to those. In order to introduce resistors, I'm going to show you the actual set of resistors that I purchased. I think I got these from Amazon as well. Some of my electrical engineering friends make fun of me for getting stuff off Amazon because you can get them from parts houses that are much better, they say, than Amazon. But for a novice like me, this does quite well. So what I want to show you is I ordered this one. Has a bunch of different values. In this laboratory, we're only going to use 1 kilo ohm resistors, but when I order them, they actually come in packs. So this is a 100 ohm resistor. That's one, I'm guessing that's mega perhaps. Yeah, 5 kilo ohm resistors, 6 kilo ohm, 150 ohm. So they're all kind of labeled there. But there is a practice in engineering which is to use color codes. You kind of see this here. I buy precision resistors, at least I did for this pack. I'll show you in a second what less precise resistors look like. The usually blue resistors that have 4 lines on them are 1% or 2%. They're called precision resistors, and you kind of see more about how that color coding works. We'll talk about that in just a bit. So what I wanted to show you on the resistors that we're going to use in this packet, these things look like this. And if we zoom in to this, I'll see if I can do this for you. It's really hard to see in this camera that the color of those. So there are 1, 2, 3, 4, 5 different little marks on that resistor. And those marks give us a sense of the resistor's value, so how much resistance it provides, as well as the precision. So when these things are manufactured, it's not a perfect science. So there are some errors, and scientists that make these can quantify how imprecise the actual stated value of this would be, and then they will encode that information in a band. Let me go ahead and show you what I mean by this. So this is a precision resistor with 5 bands. I also have a set of non-precision resistors, so I think this is a 1% tolerance. These kinds are kind of fun. These are actually the first type of resistor I've ever seen, the little tan ones. You'll see that only has 4 bands. I have a nice visual of some of this information in a workbook that I've created for my users because I recognize not all people are fluent in this before we start. So in particular, you kind of see there's 3 different versions of resistors that we're going to refer to in this work. One of them is an actual resistor, and this one's kind of nice. I touched it up in Mac Photos. You can clearly see the bands 1, 2, 3, 4 with a 5th band for precision. That is a real resistor. I took that phone with a picture with an iPhone. This thing right here, the figure 9B, that is a virtual resistor that I made in a computer programming software called Fritzing. So let me go ahead and open that for you. I actually downloaded Fritzing back when I did. It used to be free. I think they now charge like an $8 fee. For those of you that are interested in becoming electrical engineers, or for those teachers who want to make some of this on their own, this is this software. What's really nice about this software is it allows you to create kind of really nice looking breadboards quickly. So over here you can kind of see that I forget how you do this. There's a way to change. Yeah, so see this if I go from full to half breadboard, and I forget the difference between just regular half. Oh, I think it's color. Do you see that? So this one has color in it. And then what's nice about this is I can actually like just drag and click resistors. So I can kind of just take the edge of this thing and put it over here, and take the edge of this thing and put it over here. And not only that, I can determine specifically what value I want. So in my case, I'm using a 1 kilo ohm. And in this case, you see the tolerance there is 5%. Well, I can tell it I like a tolerance 1%. And then it's kind of funny on this one. THT means through-hole technology. That's really having to do with how you mount it on a printed circuit board. SMD means surface mount device. These are all THTs, but the I forget how to do, 5-band. So if I change to 5-band, you see how that turned to blue right there? I wish I could zoom in on this thing. Maybe if I do, yeah. So check this out. If I have a 4-band resistor, it will go to that nice tan thing. And we're actually looking at on the, yeah, see that? So that's a 4-band resistor. And then Fritzing says like, oh, if you want a 5-band resistor, you can actually tell Fritzing like, please do a 5-band resistor, and it actually gives you that same thing. And this is a really, really nice way to make circuit diagrams. In fact, you'll see, wiring diagrams. So diagrams that allow you to wire stuff quite quickly. And so this is a way to kind of play with that. We'll talk more about that, but I just wanted to give you a sense of how did I make those diagrams? And then 2, what do the actual physical resistors look like? The next thing that I think is kind of important on this is to understand how these color code situations work. And to do that, we're literally just going to pull up Firefox combined with DuckDuckGo. I'm all about privacy. You're going to hear me say this 1,000 times. I only use Google when I absolutely need to. So in this thing, we're going to do resistor bands chart. Already fills it in, and then go to images. And this one I actually really like. Let's see if I can find the one that I like most. Yeah, this is kind of nice. This one's also kind of nice. Yeah, it doesn't, I mean, at some level. So for the 4 bands, you can kind of see the first band is the first digit, the second digit, the multiplier, and the tolerance. So for example, if we had red, black, red, so red is 2, black is 0, red is 100. So 20 times 100, that's a 2000K. So this is a 2 kilo ohm or a 2000 ohm resistor because it's 2000. And then the tolerance on this one, it looks like it's kind of gold. So that's actually plus or minus 5%. So if I were to actually run this through an Ohm's law experiment, this resistor would be 2000 ohms, 2 kilo ohms within 5%. So it might go up, well, let's see, 2 times 5 is 10. So it would go up by like 50 or down by 50 if I were to actually measure that. And so that's what those codes represent. Some of these diagrams you'll see actually have both the 4-band and the 5-band. 5 bands allow for a little bit more precision. So it's the first digit, the second digit, the third digit, the multiplier, and then the tolerance. So we could actually take a look at this. Red is 2, orange is 3, purple is 7, black is 1. So this is a 237 ohm resistor, and the tolerance is 1% because that tolerance band is brown. We don't actually have to worry about any of that because our resistors are going to be constant. They will have all the same resistance values. So specifically, let me see if I can get, there it is. We will also always go brown, black, black, brown. So if we were to go back to our little bands there, so remember, first brown, so that's 1, 0, 0 times 10. So that would be 100 times 10 is 1,000. That's 1,000 ohms. 1,000 ohms is 1 kilo ohm. So that's 1,000 ohms, 1 kilo ohm. And the fact that that little 5th band, the tolerance band, is brown means that this is a 1% resistor. So we expect this thing to be accurate within 1% or 20 ohms. So it could be 20 ohms above, like 10 ohms, or 990 ohms, because it's 10% of 1,000, right? But that means that it's pretty darn precise. So we'll kind of use that as a way to build our resistance values. The last thing that I want to talk about is that in wiring diagrams, so when we're actually wiring this thing up, we're going to use a digital representation. When we build the darn thing but with our hands, get our hands dirty, we'll use the real resistor. But in an ideal circuit schematic, this diagram right here is a resistor diagram. So this actually represents symbolically the real component of a resistor. So anytime you see this little line with squiggly stuff, another line, that's called a circuit schematic, an ideal representation. And those are fundamental when we're building mathematical models of the behavior of resistors. So in this case, we have what we call a real resistor. We've got a digital representation of a real resistor so that we can communicate to others how to build stuff. And then we actually have the actual physical resistors encoded as a diagram so that we can draw stuff. So kind of a nice representation of this is this diagram right here. So in this diagram I see, I'm going to create a circuit that has one resistor. We'll label that R1. That resistor's value is 1 kilo ohm. So we just write 1K for that. That's kind of an electrical engineering convention. And then it's going to be connected to a 5-volt voltage source. So notice this is not an actual wiring diagram and it's not a physical circuit. It's an ideal schematic, a mathematical model of the corresponding electrical components. The last thing that I want to talk about relates to the actual different types of resistors here. So let me go ahead and zoom in there. When we're looking at resistors, we're going to think about some different parts of resistors. We will call this thing right there, the centerpiece, the actual functional electrical component of this, we're going to call it the body of the resistor. So that's the resistor's body, and it's kind of hourglass shaped. I don't know if you can see that. It's kind of like thicker on the outsides and kind of has a curve on the inside. So that's the body of the resistor. And then we're going to call this a two-terminal element. Two-terminal means two places that it connects to other things. This is one terminal, so the wire sticking out of one end, we're going to call that one terminal. You can also call these leads, L-E-E-D-S, leads. So this is the first lead, and then this is the second lead. So those leads are the actual physical wires that allow us to connect the resistor to other circuit components. So what I do is I actually take this lead and I stick it into the little contact strips that we saw in the last video. And then once I've done that, this resistor, the body of the resistor sits here, the lead connects to that contact strip, and then that extends that lead, that physical conductor, out over here, and the same thing's true on that side. And so we can think about every two-terminal element, and we'll start with resistors, as wire, the actual functional part, wire. Another way to say this is lead, body, lead. So the reason that that's useful, if I'm thinking about this as lead, body, lead, that's exactly what we see here in this schematic. So here you see that this is just a piece of wire letting electrons flow. Then we've got the body of the resistor in the middle, and then we've got our second lead. So when we say two terminal elements, what we mean is it has the body and it has one lead on one side and one lead on the other side. Those elements connect to other circuit elements in two places. That gives us a pretty good introduction for resistors. In the next video, we'll talk about our voltage sources as an introduction to how those things behave. So in order to understand the electrical components, the electrical properties of resistors, we actually need to understand a little bit about voltage and a little bit about current, and that's what we're going to get to in the next two videos. One voltage source, the other one current. I will see you in the next video.